explain how this lecture got here today. It was meant to be early next week as part of the introductory lectures for beginning students, but because of a time change in one of the speakers, it got plunked up here today. So I want to emphasize this is really elementary stuff, and I recommend that anyone who isn't really a beginner would probably enjoy reading the posters outside or talking more than listening to this rehash of sort of well-known kind of basic principles. So I would not be at all upset, in fact rather pleased if you're not a beginning student to go spend your time some other way. Okay. What I wanted to do was to just pick up and talk about some of the basics of atoms with radiation. I've handed out the notes that we use at MIT in our beginning course in atomic physics for graduate students. So you're welcome to have a copy of all those notes. They are kind of working notes. And to my embarrassment, I realized they hadn't been worked quite enough, that the chapter that I'll be using today has quite a few errors which I thought had been corrected but hadn't been corrected in it. So anyway, you're welcome to that. They may be helpful to you. These notes, again, are elementary notes. They involve material which is taught in the course, but which is also, it's standard. It's in all the textbooks too. The presentation in these notes is really meant to sort of follow the lectures and sort of be a learning assistant to the students. Okay, with that, I would like to pick up where I left off last week, which was talking about the interactions of atoms with the radiation field. We looked at it classically and looked at the Rabi resonance, which is in the rotating coordinate picture, which is really a very good picture for visualizing lots of effects, but not for calculating quantum mechanical effects. For instance, it's quite useless if you're trying to deal with, say, spontaneous emission. And for that, we did go through the quantization of the radiation field and wrote down an interaction Hamiltonian. And the interaction Hamiltonian of the field, well, let me just remind you again, the field that we took is the electromagnetic field can be described by a vector potential A, which is just, it has some transverse polarization to it. And we took it, just an ordinary propagating field, K dot R minus omega T. And we considered two levels, states A and B. The interaction Hamiltonian we showed of the field with the atoms is just EA over MC times the polarization vector dotted into the atomic momentum P, cosine of K dot R minus omega T. We're interested in taking the matrix element of this between the two levels. We're still talking just about a two-level system. Okay, we have an initial level over here, I, which is an atomic level, A, and the photon field has an occupation number of n. I could simply just as well write this as a simple product of A and n. And the final state over here is B and n prime. Yeah. And we're looking at the interaction between these two levels, and Yep. And I'm doing this in the dipole approximation. Remember, we transformed the momentum operator into a position operator and made the assumption that between these two states, say B, e to the I, k dot r, and A, that can be written simply as B times R times A. The argument is that K over here, 1 over K is the wavelength of light. This radial matrix element involves two states in the atom. The atom is small, the wavelength of light is long, and so that this is simply 1. Now, in some cases, that matrix element is going to vanish. Okay? In that case, you go to higher order terms. But this is the most common type of radiation. It's simply going to be electric dipole radiation. Go to the next order term. If we expand that and take the next order term, we would find that there are matrix elements of the magnetic moment operator and also the electric quadrupole operator, and they're going to be smaller than this by roughly a factor of alpha. So the next radiation processes are going to be smaller by alpha squared, and you go to higher order terms, they'll go to alpha fourth. Okay, so with this, the matrix element that we want in the presence of this field from a final state over here. The final state, the interaction Hamiltonian, and the initial state is just going to be equal to, well, we're going to take, at least for now, that E dot R is simply going to be equal to Z. So RAB simply goes over to ZAB. This is just to follow the notes and to make it a little bit simpler to write, but we can put back the full polarization later if we want. And this becomes then minus IE, this is the electron charge, ZAB times the square root of h bar omega over 2 epsilon naught V times n prime A e to the minus I omega t. This is the annihilation operator over here, minus a dagger e to the plus I omega t times n times e to the minus I omega AB t. I said that there are some problems with the notes over here, and one is that this factor is wrong in quite a number of equations. I think I made a list of them. This is written incorrectly in equations 7.48, 49, and 50. This is part of a conversion from Gaussian units to SI units, one of the casualties that got stuck in there. Anyway, this is what it should be over here. And if we look at this term over here, since this is the a creation operator, no, this is the annihilation operator over here. This is that n prime is going to equal n minus 1. So this corresponds to, over here, to absorption. And here, the selection rule on this is going to be that n prime is equal to n plus 1. So this is the emission term. Now, this is only going to cut ice if the time dependence is 0 or very, very weak. So this is going to be, this term over here says that omega is going to equal omega AB. And let's see. Absorption. Hold it, have I got a wrong thing here? Says the emission is over here is omega is equal to omega AB, and that says that E sub B is equal to E sub A minus H bar omega. And this, omega is equal to minus omega AB. Yep, correct. And then this, or EB minus EA over H bar is equal to, that's minus omega AB. And this says that E sub B is equal to E sub A plus H bar omega. Yeah. So energy is conserved as we would like it to be. Okay. When we put this in, we have that F, H interaction, and I then is going to equal minus, again, this B factor I, E, Z, ZAB times H bar omega over 2 epsilon naught V. And then we have times the square root of n times delta n prime and n minus n prime and n minus 1 e to the minus I omega t plus the square root of n plus 1 times delta n prime and n plus 1 e to the I omega t e to the minus I omega bt. Okay, so this is the absorption term over here and the emission term over there. And this says that the absorption rate over the emission rate is going to go, it goes as the square of these terms over here. So it's going to go as n over n plus 1. Okay. Well, that's a famous result which actually was calculated by Einstein in 1917. The real significance of it is this n plus 1 over here. Maybe I should write it the other way around. The emission rate over the absorption rate is n plus 1 over n. No. The fact that we have more emission than absorption in the system means that you have spontaneous emission. Means that we're going to have an emission process even in the case where n is 0. That bothered me a lot, I must say, when I was starting to learn this subject and how spontaneous emission could occur. It seemed to me sort of a swindle that somehow you have nothing in there, you just have the vacuum, and an excited atom is going to radiate down to the ground state. Well, over the years, that's become much simpler because the subject has grown called cavity quantum electrodynamics. And cavity quantum electrodynamics involves radiation fields that are much simpler than the normal radiation fields that we look at. And that's because it involves space, which is much simpler than the space that we look at. It involves space with just one single mode to it altogether. So what I want to do is just to look at the motion of the system in a vacuum. A vacuum being a radiation vacuum. Namely, I'd like to take a look at a two-level system. And what happens to it if you put an atom in there, but there's no field in there at all. So we're going to have a two-level atom, and I'm going to, say, put it in the excited state and put it into the cavity. Now, according to the conventional theory, this excited atom is going to radiate down. And it does. The question is why? Well, you could argue that's a metaphysical question. It's just the equations say it should, so it does. But let's look at a vacuum field with the occupation number of 0. And I would like to look at this matrix element between the final state and the initial state. I hope the board doesn't need to be visible. This stuff is in your notes, so, but I hope it's visible. Okay, this is equal to IEZAB times the square root of h bar omega over 2 epsilon naught v. And I'm going to call this just simply H0 Fi. The 0 indicates this is the interaction Hamiltonian with an occupation number of 0 in the system. So I would like to look at two states. I'm going to look at the state A, and this is B, and they're separated by h bar omega. And the initial state here I will take as, I'll take it A plus h bar omega, A plus 1 photon, and the final state over here I'm going to just simply take as state B. And the way I've drawn it, these two states are degenerate. Okay? Well, when you have degenerate states, but there's an interaction between them, first order interaction between them, you split the degeneracy. Yeah. So the eigenstates of the system, then, okay, I mean, here are my two states. This is A and 1 photon, and this is, if you like, B and 0 photons. These are the eigenstates of the system, but when I put on the, this interaction Hamiltonian, they're going to be split. And so the eigenstates then, these are the base states. They're not the eigenstates. They're going to be 1 over the square root of 2 times I plus or minus F. And they're coupled by H0, this interaction. Yeah. So suppose we say at t equals 0, there is no photon in the cavity. Well, that means that we're going to be in a psi 0, then, is going to be, in this particular state, it's going to be 1, 0 of the one plus, the plus state over here, plus the minus state. Yeah. These are what I call the plus and minus states over here. I've just written these as plus or minus, like that. Okay, then psi of t. These are going to evolve because they're split by the interaction Hamiltonian. So it's going to be equal to 1 over the square root of 2 times, say, the plus state over here times e to the I omega over 2t, and I'll define that omega in a minute. plus the minus state over here, e to the minus I times omega over 2 times t. Okay. So the system's going to oscillate back and forth. And the splitting is just given by the first order interaction that I wrote, the H interaction. You know, the splitting is going to be twice the matrix element between them, and so that the interaction between them is given by omega naught over 2 is going to be equal H0, this interaction Fi, divided by H bar. And it's equal to E times ZAB times the square root of omega over 2 epsilon naught V. Okay. The system oscillates back and forth between them. If you look at the probability of the state, the oscillation frequency is just going to be equal omega. Namely, if I start in state 1, the probability, say, of being in state 1 is just going to go back and forth like a cosine at this rate over here, omega. Well, that's a little bit surprising. You'd like sort of some physical interpretation of that. Well, a natural physical interpretation is to say that, well, the cavity in the ground state n equals 0 is not an empty cavity. There is there's 0-point energy in there. And the 0-point energy can simply cause the atom to go from the excited state to the ground state and back. Well, it doesn't work. And the reason it doesn't work is that one is trying to apply a classical field picture to the system, which is sort of totally quantum mechanical. It's hard to get more quantum mechanical than a radiation field with just one photon in it. Furthermore, if you try to push that through, you get kind of absurd answers. It just doesn't behave very nicely, either physically or mathematically. But this has a rather simple solution to it, a simple explanation to it. H bar omega naught, that's an energy, is going to equal twice E times ZAB times omega over 2 epsilon naught V times H bar. I got that right in there. Let's see, the interaction Hamiltonian. Oh, there's an H bar in there, so there should be an H bar in here. Yeah. Suppose I write this thing as, let's see, you know, this is H bar omega naught is just, this is H bar omega naught over 2. So this, we can write this thing as twice, I'm going to write this thing E times D. This is a dipole moment. Yeah. Times a field over here. I'll put this in quotes over here, where E prime squared is equal to H bar omega over 2 epsilon naught times V. Or epsilon naught twice epsilon naught E prime squared times V is equal to H bar omega, and oh, okay, the E field has another dot. I'm off. Let's see. The dipole moment. The dipole moment times the E prime is equal to I'm just worried about, I have two factors of 2. This should be 1/2 epsilon naught times E prime squared times V is equal to H bar omega. Yes, well, I'm a factor. It's actually a factor of 4 here. Maybe I won't stop. I think it's correct. I think it's correct in the notes. So I won't stop I won't try to track down that error over here. This gives at least a physical meaning to this field. It's a field that you get having just one photon in the cavity. Well, the cavity is oscillating back and forth between 0 photons and 1 photon. But at least it has a reasonable physical magnitude. And it also shows why the system oscillates. Why does the atom start radiating when you put it in there? Well, as soon as you put the atom into the cavity, you no longer have 2 systems. You don't have an atom in a cavity. You have a coupled system. And you're not putting it into an eigenstate of the system. You could have a symmetric and an antisymmetric system, which is a superposition of the atom in the ground state and 1 photon in the cavity, and the atom in the upper state in 0. Okay? Those are the eigenstates. But you're choosing not to put them in an eigenstate. In fact, it'd be kind of difficult to make an eigenstate like that. So the atom in the cavity oscillate back and forth. Now, the question is, does this really happen? Well, yes, it does happen. This has not been seen at optical frequencies, but it's been seen with Rydberg atoms, which have very large dipole moments in cavities. The art of seeing this is you have to have an awfully good cavity. The reason that atoms don't spontaneously oscillate back and forth, but they all decay down to the ground state, is that you're always looking at them in situations of space or systems with many, many modes to them. But if you have just one mode to it, that the atom will oscillate back and forth until the mode damps out. And it takes some art to make cavities which are good enough so that the damping time is long compared to the oscillation period here. But this has been done in the famous series of experiments by Herbert Walther, and particularly Serge Haroche at École Normale, who's made an art of using these atom cavity interactions. It's sort of the basic experiment of the subject called cavity quantum electrodynamics. You have this frequency over here, omega naught, which is the vacuum. It's called the vacuum Rabi frequency. And that's what you get if you put an atom into a cavity with n equals 0. But if you put an atom into a cavity with n photons in it, the frequency is going to be the square root of n plus 1 times omega naught. This gives you an opportunity to actually measure the number of photons in a cavity. And Haroche has done a beautiful experiment in which you take a cavity in a Fock state, namely you have a distribution of photons in the cavity. Okay? And the atom in the cavity oscillate back and forth, but each mode oscillates at a slightly different frequency over here. So you get some kind of weird pattern of the atom in the cavity oscillating. Then you Fourier analyze it. When you Fourier analyze it, you find that you get a peak corresponding to each one of these ends. And from that, you can tell how many photons were in that mode. So this is a gauge for measuring Fock states. Now, this is about the simplest system that one can have. This problem was actually analyzed or proposed many years ago by Jaynes and Cummings. It's called the Jaynes-Cummings model. And they put forward it just as a purely little pedagogical model. It's a simple quantum mechanical problem that you can solve. You know, one atom coupled to one mode of the radiation field. But as is often the case, problems which look like purely pedagogical turn out to be actually practical. Now, what I'd like to do now, though, is to talk about the more important issue of spontaneous emission and how does it come about. Questions? Yeah.
Oh. What would be the difference if it were a free space? When we make the assumption of the cavity?
Oh, well, when the cavity absorbs, the oscillations simply damp out, very much as you'd expect. Okay? In fact, there's a very interesting way to approach it. If you need a cavity with a very long damping time to it. That means it has to have a very high Q, you know, the quality factor of a cavity, which is essentially the number of oscillations that the cavity goes through before it damps. Okay? You need Qs in the microwave regime. You're sort of starting out. You need Qs above 10 million or more just to see the thing at all. If you put atoms in a cavity, two things happen to the atom. When you put the atom in the cavity, as you increase the Q, first of all, the atom does radiate more quickly. This was pointed out by Purcell in 1946 in the context of nuclear magnetic resonance. He pointed out that when you have nuclei precessing in a cavity, you can neglect spontaneous emission. They will be damped by something, but not by radiation. But he pointed out that if the cavity has a very high Q, they're going to radiate more rapidly. And so that so this is sort of the primary thought in the field, which was due to Purcell, that the radiation rate inside of a cavity is essentially Q times higher than the radiation rate in space. And the reason is that the Q of the cavity sort of folds together. If you like, you have lots of modes in space. When you put them in a cavity, these modes get compressed into a very narrow width. So, and this radiation damping has been seen in nuclear magnetic resonance, even though the lifetime for one spin can be forever. If you have a whole lot of them, at some point you do need to worry about that. So, so what happens is, if you put atoms in a cavity, and look at the radiation rate for the atom, as the cavity, it damps very, very slowly, but as you put them in a higher cavity, this is the atom, and this is increasing Q. Now, what about the cavity? Cavities damp pretty rapidly, but as you increase the Q, they damp more slowly. So what happens is you have a cavity which is going down like this. This is the cavity damping. Yeah. But you increase the Q, it damps more and more slowly. Well, you can see at some point the cavity is going to damp less slowly than the atoms do. This means when the atom's in the cavity, it's giving its energy to the cavity. The cavity would like to dissipate it, but it can't do it rapidly enough, so it just gives the energy back to the atom. And you take the limit of this thing. When they're near each other, it's a bit messy, but they start a bit oscillating back and forth, and then eventually you get to the region where the atom and the cavity just oscillate. And that's what the vacuum, the Rabi oscillations are. Yeah. But What I'd like to do is look at the more familiar mundane problem of just what happens when an atom radiates in free space. Now, we have a two-level system. We could solve the atom cavity system, the vacuum Rabi oscillations, exactly because it's an exactly solvable system. It's two levels connected by a sinusoidal perturbation. But as soon as you make life a little bit more complicated, exact solutions aren't possible anymore. And you have to do the next best thing. You go to perturbation theory. So we're going to consider the system two-level atom, and we're going to consider the effect of the radiation field, and we haven't specified it as present, just exactly what it does, but that it's going to be a perturbation. And it's a time-dependent, inherently time-dependent process, although using the address-to-atom formalism makes it look like a time-independent process, but we'll just solve the basic problem. And I'd like to look at the transition rate. Say if an atom which is initially in state A is going to go to B. Well, first let's look at the transition probability by time-dependent perturbation theory, and this is just going to equal HBA squared over H bar squared times the sine squared of omega minus omega naught T over 2 divided by omega minus omega naught T over 2 squared. Now, if we look at for very short time, times are just so that this is a small number over here then. This is simply going to go as it approaches HBA over H bar squared T squared. So the transition probability starts going quadratically in time. Well, if you can think back to last week, this is exactly what happens when you look at classical Rabi resonance between two levels. You know, in Rabi resonance, you just oscillate back and forth at the Rabi frequency. If you're on resonance, and let's say we are on resonance, then you start here. Well, this is the excited state. Let's say we look at the other state, and the population just oscillate back and forth like that. And this is quadratic over here. So for very short times, the thing behaves just like a monochromatic radiation, which is applied to a two-level system. Well, that's pretty much what it has to do, because for very short times, there's no way of knowing whether or not the radiation is monochromatic or broad. For very short times, all radiation, if for a short time all radiation is spread out, or another way of saying it is that all radiation looks monochromatic. So that's how it starts. But suppose we would like to look at longer times. And when you do that, the process, you have to take a limiting process about that sine squared function, and you end up with Fermi's golden rule. If you'd like to get a stationary result, essentially it means that you have to be able to take the limiting case of that transition probability, and you have to integrate the probability over the distribution of frequencies or modes or what have you. And for a long time, then you get the transition probability, A goes to B, is HBA squared over h bar squared times 2 pi t times this delta function of omega minus omega naught. And this is one form of Fermi's golden rule. This is, in spite of the delta function, it's nicely behaved because the transition rate, which is just dw by dt, then is just equal to 2 pi delta times omega, h BA squared over h bar squared times 2 pi delta of omega minus omega naught. Yeah. So at least you end up with a stationary transition rate. Now, in order to use this, you really need to integrate over the spectrum. Okay. And the most common situation is when you have a spectrum which is described by some spectral distribution function. For instance, suppose the spectrum is described by a normalized distribution function such that f of omega times d omega is equal to 1. Typically, well, the most common one is a Lorentzian curve, but it could be anything. Here is omega. Here is the transition frequency that we want, omega naught. And the spectrum, well, I'll draw it like here. It has some width to it over here, delta omega, and it has some height over here. I drew it off-center just to indicate it can be off-center, but invariably when you use this, you'd like to center your spectrum on this. So what you have is that f of omega naught times delta omega over here is going to be equal to 1. What we mean by a normalized spectral distribution function. And when we put this in over here, or over here, we're simply going to get HBA squared over h bar squared times 2 pi times, well, f of omega naught. I hope. Yep. We can also write this thing as HBA squared over h bar squared times 2 pi over delta omega. I write it this way because there's another way to interpret this, which is really quite handy. This, again, it's the matrix element coupling the two states divided by h bar. It's what we call the Rabi frequency. Yeah. So this can be written as 2 pi times omega Rabi squared over delta omega. Or better, 2 pi times omega Rabi times omega Rabi over delta omega. The reason I kind of like to write it this way is that it emphasizes this prime coupling of the atom to the radiation field, the Rabi frequency. It sets the scale for things. If you just have one mode present, the transition rate is given by the Rabi frequency. Now we have a broad spectrum present. If you like, it dilutes the Rabi frequency. It isn't as effective. It's decreased by this ratio over here of the Rabi frequency to the spectral width. Okay. If the spectral width is narrow compared to the Rabi frequency, then this this perturbation theory no longer works. It becomes a time-dependent process. But in general, the spectral width of most sources that you have, except perhaps for laser sources, is always very large compared to the Rabi frequency. So we can now put these together to look at the case of spontaneous emission. let's look at the absorption rate. Gamma absorption is equal to 2 pi times HBA squared over H bar times delta of EB minus E sub A minus H bar omega. And when I integrate this over any distribution of energies which are present, it just becomes 2 pi times HBA squared over H bar squared times rho of the rho of the spectral density of modes at the not of modes, of energy at the transition frequency. I've used the fact that the density of energy over here is just going to be 1 over H bar times rho of omega. Okay. This then becomes 2 pi times HBA squared over H bar squared times n of omega. This is the distribution of photon modes over there, which is equal to pi times E squared times the matrix element squared, polarization dotted into R squared over epsilon naught times H bar V times omega naught times n of omega naught. Yeah. Now, n of omega naught is just the density of modes that the atom has for absorbing into. And that can be shown. It's shown in the notes. It just, counting the modes in a box. You'll impose periodic boundary conditions, and the density of modes then is given by, this is the mean occupation number per mode times V times omega squared times d solid angle omega divided by 2 pi cubed times c cubed. And when one puts that in, the absorption rate then becomes the mean photon number n bar times omega cubed times the square of the charge E squared times E dot R squared divided by 8 pi squared epsilon naught H bar C cubed. Times, I put in the density per unit solid angle, but you have to integrate over the angle. Okay? When you do this integral over here, you get 2 for the two polarizations. And then when you do the angular integral, you get 2 pi. And when you do this, when you integrate this over direction, it's a cosine over the direction, it gives you 2/3 times 2/3. So this is just equal to 8 pi over 3. So when this is all put together, you get 1 over 4 pi epsilon naught times 4/3 omega cubed E squared times RBA squared times n bar. Again, in the text, this factor is missing. Missing in the notes. Was a victim of the change in system. Okay, now this is the absorption rate. The emission rate is just going to be equal to n bar plus 1 over n bar times the absorption rate. And this goes then in free space when n bar goes to 0. This is what we call the spontaneous emission. Okay. So gamma spontaneous is just this thing 1 over 4 pi epsilon naught times 4/3 omega cubed E squared R dA squared over there must be a omega squared over C cubed downstairs, I guess. Right down there. Yeah, it's H bar C cubed. This is a very important result because spontaneous emission is so important. Without spontaneous emission, the world would never have come to equilibrium. Okay? In any measurement process, if you try to track down the limitations to your measurement, you'll eventually find that the limitations are set by spontaneous emission. It's the fundamental irreversible process in nature. Right? Atoms radiate into a vacuum, and this is a vacuum that we're talking about here. No photons around. They don't get excited by the vacuum. Okay? So it plays a very profound role in physics. And it's fortunate for us that it has the size that it has. Now, what I want to do is to argue that this is a very small rate. Okay? It's a very weak rate. If it were a strong rate, life wouldn't be at all like it is right now. It's not apparent at all because of the units that we have over here. This is sort of an insult to aesthetics, but it's legally required in the SI system. Right? And these quantities right now don't have transparent value, although you can certainly plug them in. But let me just digress for a second and write these in more sensible units for these problems, which are atomic units. So let me just briefly put down what they are. Atomic units. Well, in atomic units, E is equal to H bar is equal to 1. So the mass of the electron is also equal to 1 in atomic units. The unit of length, it's 1 Bohr, which is, I think, 0.6 times 10 to the minus 9th meters. The unit of energy is the Hartree, and that's 27 electron volts. I like to think of it as alpha squared times mc squared, where, of course, alpha E squared over H bar C is the fine structure constant, 1 over 137 point blah, blah, blah. Yeah. This being the case, you cannot take C as as 1 like you do in particle physics. In fact, the unit of velocity in atomic physics is the unit with which the electron goes around in the first Bohr orbit. The unit of time, well, 2 pi times the unit of time gives you the period of the electron in the first Bohr orbit. So it turns out the unit of time, it doesn't have a special name to it, atomic unit of time, is just, it's about, it's roughly 0.6 times, no, it's about 6 times 10 to the minus 17th seconds. Okay. Now, frequency. Well, atomic frequencies are of the order of 1 atomic unit in these units over here. Not quite. The binding energy of hydrogen is not 1 atomic unit. It's 1/2 atomic unit, correct? Because it has potential energy, as kinetic energy. The binding energy of, say, the hydrogen atom is about 13 electron volts. Typically, optical transitions are somewhat less than that. Lyman alpha is about 3/4 of that. But suppose we take this thing in atomic units over here. We can neglect that, we can neglect this, we can neglect that. What we have downstairs is alpha cubed. Upstairs we have omega cubed. We have the RBA squared. Well, in atomic units, this is typically of the order of 1 atomic unit. You know, it's atomic radius. So this is going to be about 1. This thing over here, well, let me pull this out a different way. Let me talk about the ratio of the frequency to the decay rate. This is what we call the Q for a harmonic oscillator, the quality factor of a harmonic oscillator. And this is going to be equal to 1 over alpha cubed. I have omega, be omega squared there, and RBA, I'm just going to take this about equal to 1. So, and for omega, well, I could take it 1, but let me write this thing. It's not going to be bigger than 1/2, so it's going to be 1/4 times alpha cubed. And this turns out to be something of the order of 10 to the 7th, 10 million. Now, in fact, in most atomic transitions, it's much higher than that because the frequency is even smaller than this over here. Let's see if the frequency, the frequency is smaller, makes this thing bigger. But it means that radiation is a very weak process. Okay? And the reason I say that's helpful for us is, well, in atomic physics, we like to measure things precisely. The spirit of the school is that we can now look at many body processes with a great precision. All the precision in atomic physics comes from the fact that you can measure spectral lines very precisely. You can do that simply because they're so weakly coupled to the vacuum. If we were more strongly coupled to the vacuum, it would be a much messier world. If we were very strongly coupled, there wouldn't be a world at all. So it's a very happy thing for us that we're coupled to the vacuum so weakly. But it's also very interesting that we are coupled to the vacuum, because that gives rise to quantum optics, cavity quantum electrodynamics, and sort of all the really interesting areas of, or at least some of them, of contemporary atomic physics. In any case, here's how we can calculate the spontaneous emission rate. And what else did I want to say about it? Oh, yeah, just one other thing, that this, of course, has a famous name, the decay rate. This is, of course, the same. This is the Einstein A coefficient. Now, in any process of absorption or emission, we have a matrix elements which comes in, and I've been talking about the dipole approximation over here. That H always involves a factor of the form of E dot R AB squared, which I can write as, state B, this polarization vector dotted into R and A. This is a transverse vector over here. It's transverse to the radiation field, but it can have components in three directions, depending on the orientation of the system. This, of course, in fact, let me just write this thing as E, I'll take this outside, dotted into B times R times A squared. This matrix element over here imposes selection rules. I'm not going to talk about them in any great detail because it's a pretty straightforward business, but just to remind you of where it comes from, that we can write R over here. I could write it as X, Y, and Z, like that. I could also write it like this, 1 over the square root of 2 times X plus IY, Z, and 1 over the square root of 2 times X minus IY. And this looks very much like the same form of, angular momentum raising and lowering operators, J plus, JZ, and J minus. In fact, you can show that these transform the same way. Right? Now, there are two important selection rules which come up in this. One is that these states are going to have even or odd parity. And the parity operators discussed in the notes, one can prove that. But basically, the Hamiltonian that we have, the Coulomb Hamiltonian, is invariant if you invert the signs of all of R. If R goes to minus R, the Hamiltonian H of R is equal to H of minus R. As a consequence, all states are even or odd in parity. Even states, well, obviously even states don't change the sign when you invert R, and the odd states do. S states are even states. They're spherically symmetrical. P states are odd states because they stick out on one side with one sign and the other side with the other sign. Okay. So the states are states of definite parity. This matrix element over here also has a definite parity. This is an odd parity. As a result, we can only have matrix elements between states of different parity. Namely, if you multiply an odd parity state by this, you get even parity. And it will have a matrix element to an even parity state. And similarly, if you multiply an even parity state, it becomes odd, and that will have matrix elements to states of odd parity. So the selection rule here is that one is opposite parity states. And also because of the nature of this operator as a vector operator, you can prove that it will only have matrix elements between states whose angular momentum, total angular momentum to delta J can be 0 or plus, or it can be 0 or 1. And M, which is the eigenvalue of JZ, delta M can be -1, 0, or +1. You're probably familiar with those. It's sort of worked out in the text. I just mention it for completeness, because you can't neglect it totally over here. There's the theory of angular momentum is beautifully worked out. One can write the general forms for operators such as this and the higher order operators too in terms of angular momentum vectors. So I just wanted to mention this really for completeness over here. Now, there are lots of other topics which are directly related to this, so I was sort of debating as to what to talk about. Line shapes and absorption and emission, the effect of motion on things, Doppler broadening, Dickey narrowing, the role of confinement, the role of radiation when you're confine things like in optical lattices, But I thought that one thing that really would be very relevant right now, I would like to talk briefly about the origins of forces on atoms, because of course that's what the ultra-cold atoms uses these forces to cool the atoms, to grab them, and to manipulate them. So I'd like to make just a quick foray into the origin of the optical forces. Particularly, we saw these marvelous pictures of atoms being manipulated in optical lattices, which are these sort of ideal kind of egg crates in space, which hold the atoms very nicely and allows you to do sort of incredible experiments. It'd be sort of nice to know how they work, where they come from. So I want to talk about that. And in fact, there's a beautiful paper on the subject by Jean Dalibard, that I won't embarrass him by saying it's really a superb paper by Jean and Claude Contanucci. A paper maybe ahead of its times. It was done in 1985, as this field was just starting. But it gives a beautiful formalism for explaining lots of these things. So let me just list here as a reference. It is Dalibard and Contanucci. Journal of the Optical Society of America. It's JOSA B. It's volume 2, page 1707, and the year is 1985. It's a beautiful paper because it explains light forces so elegantly and also sets out the whole formalism of the dress-to-atom picture very beautifully. So what we want to do is to talk about, first of all, again, it's a two-level atom. Levels, we just call them levels A and B. No, I'll follow the notation of that paper. They call it E and G, excited and ground, although those are somewhat misnomers. And a laser field. And the laser field has n h bar omega, n photons in it of h bar omega. In this treatment of the dress-to-atom picture, we're looking at essentially classical fields. You can extend it to quantum fields, namely where n is small, but n, we're just going to treat it as a constant. It's a large number. Okay. And one wants to look at the energy levels for this. Well, here is one level of the photon field. Let's put in h bar omega laser. There's another level of the photon field. Let's say this is a level with n minus 1 photons, and this is going to have n photons, and then this is going to have n plus 1 photons. Now, the laser field is not taken to be resonant with the atomic transition. We're going to introduce an offset, delta, which is going to be equal to, let me get the sign right over here, omega laser minus omega naught. We can change the sign, but for the point of view of this, I'd like to make it look like that. And then I would like to add the energy of the atom in it. So here we have this. Now, here is the atom over here, which is this is the excited state of the atom, and this is n minus 1 photons over here. That's going to be degenerate with the ground state of the atom and n photons, like that. And the splitting that we have over here is just the difference in frequency between the laser You know, if the laser were exactly two non-resonants, these would be degenerate with each other, but it's a bit off of resonance. And similarly, over here, we're going to have levels over here. This is going to be the ground state and n+1 photons, and this is the excited state and n photons over here. Yeah. Now, this is just an energy level drawing. There's no interactions between these. Again, we have delta like that. Now, suppose I put on the interaction between these states. Well, it's going to be an off-resonant, if you like, an off-resonant Rabi picture. We have two discrete levels over here. We're applying a frequency which couples these levels, but it's not on resonance, it's off resonance. So what it's going to do is, let me just look at these two levels over here. This level over here is going to be split up like that, and this is going to go down there like that. And the splitting between them now is going to be h bar omega Rabi, which is h bar times the square root. I'll write this thing as omega 1 squared plus delta squared. Omega 1 is the interaction of the atom with the moment. It's just mu e divided by h bar, just the thing we introduced in, I think, in the first lecture. So now we have splittings like that. Now, this was the ground state over here, and this is the excited state over here, but this is coupling the two states, so they're no longer pure states. Okay? So we're going to call this state over here state 1, and we're going to call this state down here, we're going to call it state 2. And 1 over here is going to be equal to, well, I'll just write this thing. It is going to be equal to, well, it's just state 1. Now, what are the energies of these states? Well, E1, it's going to be the energy of the photon field. There I can write it just as n minus 1 times h bar omega minus h bar delta over 2. That is just the energy, if you put it in, that's just the energy of this field over here. And then it's going to be plus h bar over 2 times omega Rabi. And the other state over here is going to be equal to, again, n minus 1 times h bar omega minus h bar delta over 2 minus h bar over 2 times omega Rabi. Now, all we've introduced is a energy splitting between them. But when we've introduced an energy splitting between them, we're introducing forces on the atoms. Okay? If an atom comes along here and goes into this field, this atom is going to increase its energy. If it increases its energy, it's going to be repelled by the field. If it comes into the field and on this level over here, its energy is going to go down. It's going to be drawn into the field. Okay? Whether it's repelled or attracted, it depends really on the sign of delta over here. It'll turn out that if delta is negative, if you're tuned below the resonance, you're going to be attracted into the field. But there's another state which will be repelled from the field over here. Now, what about the effect of spontaneous emission? Because that's been omitted from this treatment over here. Well, the effect of spontaneous emission is to give one of the levels, let's give the excited level a natural width. Here are these two levels. Here are these so-called dressed levels over here. I mean, this one, as you go into the field, this one is going like that, and this other one is going like that. So here's the field. And I'm just sort of moving the atom into it. Okay? That's fine, but suppose that this atom has a big width like that over there. Okay? Well, this state over here is going to have some of that state in it. Okay? So this atom is going to be very sharp over there, but as this one gets in over here, the component of that's going to be diluted, but this one is going to start to build up. And that's because this has some of that state in it. And so that's going to make it radiate. Well, if your atoms start to spontaneously radiate, you're not going to be able to do very beautiful experiments with them. So we know the problem can be overcome because we've seen atoms sitting around in lattices for a long time. And the way you overcome it is by making sure that not much of that state gets down to this state over here. Now, it's very easy to calculate the admixture of these states. It's just a 2-by-2 problem. And this state 1 over here, it's equal to the cosine of theta, say, of the site of E and n minus 1 plus sine theta of the ground state and n. And the state 2 over here is just equal to the sine theta of E and n minus 1 plus the cosine theta of the ground state and n. So this is a mixing angle between them. We'd like to keep state 1 very pure over here, so we'd like to keep sine theta over here very, very small. Well, sine theta is sine of 2 theta is just equal to, it's just the ratio of omega 1 over h bar. Yeah. It's equal to omega 1 over omega Rabi. And we want to keep that much less than 1. Well, there's another requirement on this also. You want to have the well depth deep enough to capture atoms. You do this by turning up the field as much as you can. Of course, that makes your well depth deeper and deeper, but it also mixes more and more of the wrong state. So what you do is you go further and further off of resonance. And in fact, most of these optical traps are very, very far from resonance. They may be at half the resonant frequency. Okay? So that when the atom is in the trap, even though it experiences the effect of the other level that's present, it's what helps give rise to the interaction which traps it. It never actually enters the excited state. So the spontaneous rate that you get in the trap is just, if you're lucky, it's just the same as it is in free space. If you don't have strong enough lasers to do this and you start tuning closer and closer to resonance, which makes your trapping deeper and deeper, you also find that you start to radiate more and more rapidly. But the origin of the light trap is, again, it's just the same as the Rabi frequency. So this fundamental interaction between an atomic moment or magnetic moment, electric or magnetic moment, and the radiation field sort of characterizes light trapping, it characterizes spontaneous emission, it characterizes vacuum fluctuations. Now, there are just 5 more minutes, and I want to jump around and talk about something else. Because I can do it very quickly with a little arm waving. And this is the matter of Ramsey resonance. You've probably heard the term. You may be wondering exactly what it means. It's clearly a very valuable technique because he got the Nobel Prize for inventing it. It was invented for purposes of now an ancient world, namely doing molecular beams experiments. You know, in a molecular beams experiment, you pass atoms through a state selector. Here's a state selector. You deflect atoms. You do resonance in here, and then you have another state selector and see whether they go this way or that way, and you can tell whether you've made a transition over here. The longer the atoms stay in here, the more precisely you can see the transition. And the problem they got into in the early days on this is they tried to extend this region to make it longer and longer. And what happened was that the resonance transition just kind of washed out. And the reason is that this B field over here, it's called historically the C field. It's a uniform B. If it isn't really uniform, the frequency fluctuates all the way down and you lose it. So Ramsey hit upon the clever idea of, in this region, having one coil over here and one coil over there. It's trivial to see this from the rotating point of view. Let's go into a rotating coordinate frame, and suppose we're on resonance. Okay. But this is something which is going along at the Larmor frequency. So the magnetic moment, well, I'll draw the magnetic moment up there. And maybe it's initially pointing like that. And in this rotating frame, it just rotates down like here. If you don't stop, it'll go back up. It goes round and around. And this gives rise to the Rabi resonance, which we've looked at. Now, what happens over here is you put on a very strong field, and you let the moment go down halfway. So here it is. Okay? Then you turn this thing off, and you wait a while. And then you turn it back on, and you go down the rest of the way. Okay. What's the advantage of that? Well, the advantage of that is that as you go down the machine, if the frequency fluctuates, this is going to go a little bit too fast, or it's going to go a little bit too slow. It's going to go round, it'll go forwards or backwards like that. It might even go quite far forwards or backwards. But when you're all through, it's going to have one direction over here, and you can drive it the rest of the way down. If you're off of resonance, okay, this picture in the rotating frame over here, if you're off of resonance, this thing is going to slowly precess. You know, it'll precess a little bit later. It'll be like that. And when you precess it, when you put on your next field, it's not going to go all the way down. It's going to go to someplace else, not quite all the way down. If you wait long enough and you're off of resonance, it'll be pointing like this, and you apply your next field, and it'll precess back up. Well, it's quite easy to convince yourself that what will happen here is that if you have a curve, a Rabi curve, due to this short coil over here, which is quite broad over here, what you're going to get over here is essentially an interference pattern. The Rabi curve over here, say, goes just halfway. Well, this thing can start at 100%, and then it oscillates back and forth like that. The advantage of it, too, one is this width over here, delta omega, is essentially 1 over the total interaction time, T total. This width over here, for the Rabi curve, delta omega Rabi, is equal to 1 over, I say, the time in the short coil. Okay? And as I indicated, that say you're on resonance over here, so that you'll end up in exactly the right phase. If this thing advances, or if it fluctuates around a little bit, it really doesn't make much difference. You may lose a little bit in amplitude, but you don't get any broadening from that. So this was technically a very great advantage. Now, looking at the curve, what one is seeing really over here is an interference pattern. And this is another way of looking at what's happening in the system. There are two quantum mechanical ways for the atoms to get from here, say, over to there. It interacts with the fields here, and it interacts with the field there. All you know when you're all through, it's made a transition, say, from one state to another state. But you don't know which of these it's made a transition in. So here we have a case of two possible quantum mechanical paths from the initial state to the final state. And these paths, of course, interfere with each other. And as occurs in all interference, if you try to do some more experiment to decide whether the atom is flipped over here or whether it's flipped over there, you really don't the interference goes away. This is maybe the first example of really atom interferometry. Okay? You're interfering paths which are going through different, different paths from the beginning state over here to the end state. It gives us a way to make a coherence in the system. While the atoms are going from here to here, it's a coherent superposition of the initial state, the ground state, and the excited state. So this experiment introduced some rather fundamental ideas into physics, but as often the case is, these ideas were really rather ahead of their time, because it wasn't until much later that the importance of coherence in atomic wave functions was really established, and that the role of interferometry, of this type of interferometry, there are many different types of interferometry, but this interferometry where you're just interfering different quantum paths through a system in which other paths are the same, is a rather seminal step forwards in atom optics. So the reason I wanted to mention this is, A, it's important that many atomic clocks use this method. The fountain clock uses the method. The atoms go up, they go through a field, they come back, they go through the field again. So it's a very important practical method. And it was motivated to solve a technical problem in the lab, namely the difficulty of making very long homogeneous magnetic fields. But it also introduced ideas which became very important later on. So that's one of the nice things about atomic physics. It's filled with little nuggets there, and you may not know how important they are at first when you pick them up. But this one certainly had some very important nuggets in it. And right now the field seems to be loaded with nuggets. So maybe that's a good point at which to stop this, conclude this ABCs for atomic physics. Thank you.
Questions?
When you talked about the whole of the vacuum and the spontaneous emission, how can we see easily why the fundamental state is stable? Because with just this argument, all the states could be decaying, and why?
Was the question why the ground state is stable?
That's it.
Yeah. Well,
what is the easy way to see this?
Are you asking the question of why you don't get spontaneous absorption out of the vacuum?
Yes, this does not conserve energy, I suppose.
Well, yeah,
But
that's
the atom could
that's true. But then the question is, why should you? I mean, that doesn't show you the mechanism. Actually, the mechanism for this has puzzled many people, and you often hear the comment that spontaneous emission is induced by vacuum fluctuations, and in the cavity, you'd say the same thing. There was a wonderful analysis by Claude Contanucci and some of his colleagues, and I'm not sure just which book it's published in, which shows exactly how spontaneous emission occurs. And he finds there are two effects which give rise to it. One is the vacuum fluctuation field induces transitions, and there's a radiation reaction field. This is sort of a classical-like field, which occurs in order to conserve momentum when atoms radiate. There is a field which makes them accelerate. This is the radiation reaction field. They have equal magnitude. In the excited state, these fields add together and cause the atom to radiate down. In the ground state, they have opposite phase. They don't do a thing. And so that is the most intellectually satisfying explanation I've heard for this process.
I want to get profit from his question.
Mm-hmm.
In this thinking about the paper of Dalibard and Contanucci, can we think that the vacuum fluctuation is responsible for the stabilization of the ground state of the matter?
Not in that paper. And for stabilizing the ground state of matter, I can't really comment on that. But there is something very weird about these vacuum fluctuations. I mean, first of all, they're there. You can see the effects of them and such. But then when you start thinking about large space and maybe the universe, you sort of wonder about this infinite energy in the universe. You might wonder a little bit about the gravitational inertia due to the vacuum energy in space. You know, it gives rise to all sorts of questions. And so I don't have the answers to those questions. The last word hasn't been spoken on it. Maybe someone else has a deeper understanding of cosmology and can address the vacuum energy in space. Of course, right now everyone's worrying about dark matter and gravitational energy in space, but this is just ordinary old-fashioned electromagnetic zero-point fluctuations.
Oh, if there is no more question before we go, I would like to say some special words to Dan, because he agrees to be the director of this school. In fact, Dan Kleppner is one important personality in the atomic physics in the Boston region and in the whole United States and the whole world. He just received the most important prize in the United States, which is the White House Prize of Science and Technology. And each time we call Dan to come to Brazil and to help us improving our atomic physics, he accepted. He came to Brazil many times. And just accepting being the director of this school was already an important fact for us. And so I would like to thank you very much for that. And we all appreciate the efforts in coming to Brazil, staying more than 15 days, and giving so nice background lectures to all of us. So thank you very much for everything.